So this presentation will go over the alternating series test. So far we have many different tests for convergence. Well, here's a strategy I use in order to figure out which one's used in what order. First thing I always do is look at it and say, look at the sequence that creates the series. If the limit of those terms does not go to 0 as n grows without bound, then I use the nth term divergence test to show the series diverges. After that, I try to see if I can use rewriting tricks to rewrite the series as a p-series or a geometric series or something connected to that. And then if p is more than 1 for the p-series, it converges. If the common ratio between terms in absolute value is less than 1, then the series converges if it's a geometric series. If it's similar to a p-series or a geometric series, by like removing terms, then I try the limit comparison test. If that isn't useful, like if there's a factorial in it, then I might try comparing the series term-wise by using some kind of convergent series or divergent series and aim to use the direct comparison test. If I absolutely have to, and I've gotten this far, I'll try the integral test. And as a method of last resort, I'll try rewriting the sequence of partial sums in terms of something so that I can get a formula for the sequence of partial sums in order to find the limit directly. But the tests work only for non-negative terms, except for the case of the geometric series test where it could oscillate back and forth. So the integral test requires positive terms, the direct and limit comparison test requires positive terms, and the p-test is used on the p-series, which are positive terms. So we're really kind of limited if the series have negative terms. Now, if the series has a finite number of negative terms, we just look at the partial sum up to the point and ignore it and look at the remaining portion of the series. As long as the remaining portion converges, the original series will converge also. But what if the series has an infinite number of negative terms? So you're adding and subtracting terms in different orders. Let's consider a particular series that has an infinite number of negative terms that you're adding to the positive ones. One such one is where you add, then subtract, then add, then subtract, then add, then subtract. Or if you subtracted, then added, then subtracted, then added, then subtracted, then add, and so on. You can write those two series this way. One where you start with a positive term and one where you start with a negative term. This portion right here is what creates the plus and the minus. This is what creates the plus and the minus, because what's in back, that portion is always positive. So let's assume that you have such an alternating series and look at a sub n, the positive portion, not the portion being doing the plus and minus. Let's assume that that sequence is decreasing. Also assume that a sub n is going to 0, because if it doesn't go to 0 as n goes to infinity, then by the nth term divergence test, this entire series here would have to diverge because this portion would not go to 0. And if it doesn't go to 0, the series must diverge by the nth term divergence test. Now our two assumptions are such that if you go and rewrite them in notation, it says that if you ever take a term minus the next term in that sequence, that subtraction must be positive because the sequence is decreasing. And of course, the limit of a sub n as n goes to infinity is 0. I'm going to use these things to prove that the series, at least the alternating series, must converge. Now, the sequence of partial sums, if I can show that converges, then the series must converge also. But in the sequence of partial sums, that's S1, S2, S3, S4, and so on, I want you to consider only the even indices. That's S2, S4, S6, S8, S10, and so on. That sequence, the one with only the even indices, that thing is also a sequence. I'm going to show you that that sequence converges, and then come back and show that the sequence of partial sums converges. So consider S2, S4, S6, and so on. In general, you write that as S sub 2n, where n is some integer. So S sub 2n is the summation of a sub 1 up to a sub 2n, but where you add, subtract, add, subtract, add, subtract, because of the particular summation I'm using, where here we're starting with a positive value. But S sub n, S sub 2n, has to equal s sub 2n minus 2, because that's what s sub n minus 2 is. It's the summation of all the terms up to the 2n minus 2 index. And then you have the remaining two terms. Well, but this term is before that term. Since a sub n is decreasing, that means this subtraction must be positive. So therefore, s sub 2n is equal to some positive number plus another positive number. More importantly, that means s sub 2n is always greater than s sub 2n minus 2. So that sequence is monotonic. It's always increasing. As a sneaky little trick, notice though, s sub 2n can be written this way by just moving the parentheses and noticing that the double negation, that's what makes this positive right here, this plus a3. The reason that's important is that this term, and so on, all of those have to be positive numbers. Those have to be positive numbers because a sub 2 is going to be more than a sub 3 because a sub n is decreasing. That means this overall difference has to be strictly less than a sub 1, because I have a positive number minus a bunch of other positive numbers. So all of this makes a sub 2n less than a sub 1. The important thing there is that every single one of the sequence in the partial sums, where you look only at the even indices, s sub 2, s sub 4, s sub 6, and so on, they're all less than a sub 1, which means they're bounded. So that sequence is monotonic, and that sequence is bounded. So the sequence where you look only at the even terms, that sequence converges by the bounded monotonic convergence theorem. So I'm trying to show that the sequence of partial sums of the alternating series converges to something. What I've done so far is shown you that the subsequence formed from the sequence of partial sums, where you look only at the even indices, the sequence S2, S4, S6, S8, S10, and so on, that sequence converges to something. So I'll just write that down. So the limit of the sequence of partial sums, where you look only at the even indices, at least that subsequence converges to L. Now I'll show you that if you look at the sequence of partial sums, we look only at the odd indices, that will also converge to L. So I have to take the limit of s sub n 2n plus 1 and show you that that is L. Remember though, always for the partial sum in general, s sub n, the sum of the first n terms, is equal to the sum of the first n minus 1 terms. That would be s sub n minus 1. Plus the term I have not yet added, the nth term, which would be a sub n. So if I want to know the limit of s sub 2n plus 1 as n increases without bound, I know that sequence of partial sums can be rewritten as the sum of the first 2n terms. That's s sub 2n plus the term I have not yet added, which would be a sub 2n plus 1. But that then is two different sequences. I can take the limit of both because I know already that both converge. The limit of s sub 2n, that's L. The limit of a sub anything, as long as the index grows, that's 0, because that's what we said way back when. So, if you was to look at the limit of the sequence of partial sums, just in general, doesn't matter what the index is. Well, the index is either odd or it's even. In either case, though, that limit is L. That shows then that the sequence of partial sums for the alternating series will converge. So since the sequence of partial sums converges, the alternating series converges. That gives us this theorem. If the alternating series is such that the positive portion is always decreasing after some index, and they're always positive, and the limit of that little positive portion goes to 0, then you can say that the series converges. And in fact, if you wanted to go further, I'm just not bothering to do it, you can also show that the difference between the nth partial sum and the actual summation is always less than the next term you would have added. That's what makes this particular convergence theorem great, because it's really easy to use, And it's really simple to find a way to estimate the error between the partial sum and the sum of the series. Let's go use it on this one problem. So this is certainly an alternating series. If you were to write out the first few terms, it would look like it would be 1 minus 1/2 plus 1/3 minus 1/4 and so on. This particular series is called the alternating harmonic series. And it's once again one of those series that pops up a bunch of places, and it's good to know ahead of time if it converges or not. So, since it's an alternating series, if we define that a sub n is just the positive portion, that's not the alternating portion, it's the positive portion, just notice that it's always bigger than 0 and is always decreasing for all n bigger than 1. It's strictly just going downwards. So just by knowing that much and saying that the limit of that term as n grows without bound, since that limit 0, you can then automatically say that the series as n goes from 1 to infinity of -1 to the n plus 1 over n, that thing converges. And that's by the alternating series test. So that's great, right? It's a really super fast result. And I can even say, what if I were to add up s sub 4? So that is 1 minus 1/2 plus 1/3 minus 1/4. I'd like to know then just how close is this to the real answer? Well, to figure that out, notice that the next term I would have added is a fifth. So the difference between the true sum and the partial sum in absolute value will be less than that next term. So the error is only 1/5. So that's not that large. So the error is not that great. But this term, 1 over n, goes to 0 so slowly that I need many terms, 100 terms, just to make the error less than 100th, which means that the approximation of the sum, if I add the first 100 terms of that sum, that approximation is only within 1/100th of the real answer. That's a lot of work just to get that small error. Let's look at this series. Now, as it stands right now, it doesn't look like an alternating series, but notice that you can rewrite it as the summation as n goes from 1 to infinity of -1 to the n times n squared over 2 to the n. And this term certainly goes to 0 as n goes to infinity, so we have a chance that this series converges. It's certainly an alternating series, and this time it just starts off with a minus instead of a plus. So if you just define that a sub n is equal to n squared over 2 to the n, I think you can probably see that the series is the sequence here is certainly always positive, and it eventually is decreasing. And a sub n is certainly decreasing for n greater than or equal to, I believe it's 4. So from 4, 5, 6, 7, and so on, the sequence is just strictly decreasing. That's all you need. As long as it's true eventually, you're fine. So I can then say, since the limit of n squared over 2 to the n, as n were to grow without bound, that limit's certainly 0. You can show that by using L'Hopital's rule. Then the series, as n goes from 1 to infinity, of -1 to the n times n squared over 2 to the n, that thing converges, and that's by the alternating series test. And that's it. Let's do one more time. Now, one of the great things about the alternating series test is not only does it tell you whether it converges or not, and the test is really simple, but it also tells you an estimation on the error when you estimate the summation by the nth partial sum. Now, I want to know how many terms do I need which partial sum do I need in order to approximate the summation so that the difference between the partial sum and the summation is less than 1,000th. Now notice that this thing here, that's 1 over 1,000. Just make our life a little easier. Well, the error between the two is always less than the next term that we did not add. Well, that's the positive portion. That's this guy right here. So that's equal to 1 over. Just replace the n with n plus 1. You get n plus 1 cubed. I want this error to be less than 1,000. So if I can make this fraction less than 1,000, then by tracing it back, then the error is less than 1,000. Just solving that inequality, that means 1,000 would have to be less than n plus 1 cubed. And I don't change the inequality because I only multiply by positive numbers. And then by taking cube roots, you would then have n plus 1 has to be more than 10. And I can do that because the cube root is an increasing function, so the inequality does not change. So n must be more than 9. So if I use n is 10, the first such integer that satisfies that inequality, I would then find that the 10th partial sum, it's already within 1/10 of that summation. And in fact, if you go trace it out, s sub 10, the last term you add there, would have been a subtraction. So s sub 10 is actually below the real sum. That's it. That's all we need for the alternating series test. So in class, we'll practice some more.